So, so in our last class, so we already derived a statement. What was that one? If P star is the partition of P, is the partition of P, then your LP star F, this thing is lies between LPF to LPF plus 2KP mu. Similarly, your UP star F, this thing is lies between, this is your UPF and this one is your UPF minus 2pk mu or 2kp mu. So this thing already we derived in our last class. So what the new things we will read now? Suppose P1 and P2 are two partitions of closed AB, and let P star, this is the P1 union P2, that means P star, since this is the union of P1 and P2, I can say P star is the refinement of P star is the refinement of both P1 and P2. Okay, since it has more points than P1, so this is a refinement for P1. Similarly, it has also more point than P2 because P1 union P2 is your P star. Okay, so that's why P star is the refinement for both P1 and P2. So since P1 is a partition and P star is its refinement, so I can write this statement. Since P1 is a partition, so I can write this L P1F, this thing will be less than L P star F, since P star is a refinement for P1. Similarly, since P star is a partition refinement, means this is nothing but a partition. So since P star is a refinement of, or P star is a partition of F, so partition of function f in the closed interval AB. So L P star f is less than U P star f. Lower Darboux sum is always less than upper Darboux sum for a partition of a function f. So, and also since P star is a refinement of P2 also, so this condition holds. Since P star is a refinement of P, then U P star f is less than equal to UPF. So UP star f, this thing, UP star f, this thing is less than UPF. So what we got here? This implies, sorry, this is UP2f. Since P2 is any partition and P star is its refinement, if P star is a refinement, then UP star f is less than equal to UPF. So UP star f is less than equal to UP2f. So what we got here? This implies LP1f is less than equal to UP2f, where P1 and P2 are any two partitions. Where P1 and P2 are any two partitions. So what we got here? So whatever the partitions you are taking, lower Darboux sum never exceeds upper Darboux sum. So what we got here? Whatever lower Darboux sum never exceeds upper Darboux sum. or in the reverse way you can say that the upper Darboux sum is always greater than equal to lower Darboux sum, whatever the partitions you choose. Okay, so similarly also I can say a lower Darboux integral is always less than equal to upper Darboux integral. So where f is a partition, f is a function and closed f is any of its, and closed f is the interval. So how will show this thing? From this thing, what we got the lower Darboux sum. This one. So now our aim is to conclude this thing, how the lower Darboux sum is always less than equal to upper Darboux sum. Similarly, the lower Darboux integral is always less than equal to upper Darboux integral. So now we have the LP1F, this thing is less than equal to UP2F. So that means we can say LPF is bounded above by UPF, or UP2F is bounded below by LP1F. So if I will make this P2 fixed, making P2 fixed, P to the partition P2 fixed. Now taking since your LP1F is bounded above by this one, now taking the supremum of, what we will get? So keeping P2 fixed, taking the supremum over all partition P1, taking the supremum means your least upper bound, supremum means least upper bound. Since LP1F is bounded above by this UP2F, so we can take the supremum means your least upper bound over partition P1, then the supremum of LP1F, what can we say this thing? This is the lower Darboux integral. So directly I can write this is the lower Darboux integral of A to B f dx. So this is the lower Darboux integral of f dx. So this thing will be less than equal to UP2F. Since I kept my P2 fixed, so that means this is a just constant. So if you will take the supremum of left hand side over the partition P1, then this is your lower Darboux integral. Similarly, now we can say our UP2F, this is bounded below by this quantity, the lower Darboux integral of f dx. Similarly, since it is bounded below, we can take its infimum. Now taking infimum of both sides. So what we will get? This is the constant integration of lower Darboux integral of f dx, and the infimum of this one, this is nothing but the upper Darboux integral of f dx. So this include. So now I'll go to what will be our Darboux integral, Darboux theorem. So what is your Darboux theorem? So what is your Darboux theorem? If f is a bounded function on closed AB, if f is a bounded function, f is a bounded function on closed AB, then to every epsilon greater than 0, then to every epsilon greater than 0, there corresponds delta greater than 0 such that UPF is always less than equal to upper Darboux integral of f dx plus epsilon and your LPF, this thing is less than equal to, and this one is your greater than equal to, this thing is your greater than equal to lower Darboux integral of f dx minus epsilon. And for every partition P, P of closed AB with norm mu P is less than delta. So what is your Darboux theorem? If f is a bounded function on closed AB, then for every epsilon greater than 0, there corresponds delta greater than 0 such that UPF is always, you can say this is less than equal to, or you can give the straightly less than or strictly greater than. So here UPF is strictly less than upper Darboux integral of f plus epsilon, and your LPF is greater than equal to lower Darboux integral minus epsilon for every partition P of closed AB with norm mu P which is less than delta. So now comes to its proof. Now since f is a bounded function, this is given f is a bounded function on closed AB, so we can write, since f is a bounded function on closed AB, there exists a positive number or positive real number k such that your f of x modulus is less than equal to k for all x belongs to closed AB. Since it is bounded, this is its definition. And also we know again, since your upper Darboux integral of f dx, this is your infimum of UPF, where P is any partition. So also we know this thing, infimum of upper Darboux integral of f dx, this is the infimum of UPF. So also we know this thing. So what can you say? Therefore for every epsilon greater than 0, there exists a partition P1 whose points are a equal to x0, x1, x2 dot xn is equal to your endpoint B. There exists a partition P1 of this thing, P1 of closed AB such that UPF is less than this upper Darboux integral of f dx plus epsilon by 2. So this thing we already discussed. Since upper Darboux integral equal to infimum of this thing, so for every epsilon greater than 0, there exists a partition P1 such that UPF or UP1F is less than this upper Darboux integral plus epsilon by 2. Since this is the infimum, if you will take infimum, this is the least upper bound. So if somebody will say no, if I will add some epsilon by 2, this will be the least. Obviously we already discussed this is not least if you will take something. then there will be some up which is less than this one. So what can you say more from here? So here the partition P1, here the partition P1 has this is small p minus 1, sorry, this is let this be xn, xp, x1 x2 dot dot xp which is your b. So now here the partition P1, here the partition P1 has p minus 1 more points besides a and b. Since there are p plus 1 points, so if you will remove this x naught, or if you will omit this first point and last point, then there are p minus 1 more points beside a and b. So let delta be a positive number, such that 2k p minus 1, this is small p minus 1 to pk mu, this is your norm. So in place of this one, we will take this is delta, because we already took here in the given question norm mu p is less than delta, so we will choose delta, because we already know this thing 2pk mu, we are already acquainted with this one. So 2pk mu, in place of p we will write p minus 1, and in place of mu which was your norm, so here the norm is less than delta, so accordingly I am choosing this thing for your delta. So delta is a positive number such that 2k p minus 1 delta, this is your epsilon by 2. And if you will see where how I am choosing this thing, from the starting I already told you this is your how this 2pk mu is here, 2pk mu. Okay, from that thing I am comparing my norm here, since norm is your norm mu p is less than delta, so for norm I am using this delta, and now I am choosing this delta in such a way that 2k whole into p minus 1 into delta, this is your epsilon by 2. So this is the condition of delta. Now let p be the partition such that this mu p is less than equal to delta, whatever the delta we are choosing in which this condition. So I am writing this thing again. So we are choosing delta, this is 2 p minus 1 whole into delta, this thing equal to epsilon by 2, 2pk, sorry, this is your 2k whole into p minus 1 into delta, this is your this thing, and your delta is nothing, this is the delta is this one, norm mu p is less than delta, this is the conditions of delta. So and before that we already know that if p star is the refinement of here p is a partition and p1 is also another partition, so if you will use that condition, let p star be the what is the refinement. If p star is the refinement of both p and p1 such that your p star is equal to p union p1, so since p star is the p union p1, we can say p star is the refinement of p, and also p star is the refinement of p1. So first I will start from here. as P star is the refinement. This is the refinement of P having at most P minus 1 points more than P, therefore we can write this thing also we have written before. I'm just writing this thing here. U Pf minus 2k P minus 1 mu, sorry, in place of mu we are writing delta, 2k P minus 1 delta. This thing is less than U P star F. Before that was 2 pk mu. In place of mu we are writing here delta, and in place of P we are writing P minus 1 because there are P minus 1 points more than. That's why this is the less than equal relation, and this thing is also less than your U P1F because U P star F, and this is U P1F because P star is the refinement of P1. So we can add this thing. This thing is less than equal to U P1F, and your U P1F, this is less than equal to. So you have your notebook, you can compare this thing already studied. So this is your upper Darboux UP1F. This thing is less than equal to the upper Darboux integral of f dx plus epsilon by 2. This thing is here. So finally you can write all these things. UPF minus 2k P minus 1 epsilon, 2k P minus 2k P minus 1 delta. This is your epsilon by 2. So if I will take this thing to right hand side, so what will happen? This is your UPF is less than equal to upper Darboux integral of f dx plus epsilon by 2 plus epsilon by 2. This value is epsilon by 2. This thing already taken here, or accordingly we choose that delta. That's why, so that in place of this thing we will put our epsilon by 2, so that our final answer will be your UPF. This thing will be less than upper Darboux integral of f dx plus epsilon. So here UPF is less than this one. So that was our question. UPF is less than this one, and whatever the conditions of P, here the partition P is chosen in such a way that norm P is less than delta. So we can say for each partition P, or for every partition P, whose norm mu P is less than delta. Previously we know already this thing. There exists a partition P such that there exists a partition P1 such that UP1F is less than this upper Darboux integral plus epsilon or plus epsilon by 2. This thing we already know before. UP1F, there exists a partition P1 such that UP1F is less than equal to the upper Darboux sum of f dx plus epsilon or plus epsilon by 2. These things we already known previously from the definition of upper Darboux integral, since upper Darboux integral is your infimum of UPF. And what is new things in the upper Darboux in this Darboux theorem? It says this thing holds. This is not for a single partition P. This thing holds for every partition P under this condition. For those partition P whose norm mu P, this thing is less than delta, and delta satisfies this condition. That means this delta depends upon this epsilon, where this delta satisfies 2k p minus 1 delta, this thing is less than epsilon by 2. So if delta satisfy this condition, then those partitions p with norm mu p less than delta, if this condition holds, then we will say those partitions which satisfy this condition, at that time your UPF is less than upper Darboux integral plus epsilon. And similarly we can prove for every partition p with norm mu p less than delta, your UPF is greater than lower Darboux integral of f dx minus epsilon. So this thing completes. Then conditions of integrability. Okay, I will read. If there will be any doubt, then you will ask me. Then condition of integrability. Conditions of integrability. We already know one conditions of integrability. Now we will study another condition. So what we know the before was the lower Darboux integral equal to upper Darboux integral, then that is your integrability condition. That means if this lower Darboux integral equal to upper Darboux integral, then it is integrable. That was you studied before. Now we will study another integrability condition. Then write down first statement. This is a theorem, a necessary and sufficient condition for the integrability. A necessary and sufficient condition for integrability of a bounded function. Integrability of a bounded function f is that to every epsilon greater than 0 there corresponds delta greater than 0 such that for every partition p of close AB with norm mu p less than delta, here UPF minus LPF is less than epsilon. So this is a necessary and sufficient condition. That means this is a if and only if condition for the integrability of a bounded function f is that, so a function f is bounded and then it is Riemann integrable if and only for every epsilon greater than 0 there corresponds delta greater than 0 such that for every partition p of close AB with norm mu p less than UPF minus with norm mu p less than delta, UPF minus LPF is less than epsilon. So if this condition holds, then f is integrable, or if f is integrable, then this condition satisfies. So this is another condition of integrability. That means f is integrable if and only if UPF minus LPF is less than epsilon. Now comes to this necessary part or this forward part. So given here is f is integrable. The integrability of a bounded function f. That means given that f is bounded on closed AB and f is integrable. So if f is integrable, then what can we say? Before that we already know only one condition. So f is integrable, that means the lower Darboux integral is equal to your upper Darboux integral. That means lower Darboux integral of f dx, this is the upper Darboux integral of f, and this thing is equal to your whole integral of f. So if it is integrable, then this condition holds. Now let epsilon greater than 0, then by the previous Darboux theorem what we know, let epsilon greater than 0 by Darboux theorem or by the above Darboux theorem, we know that there exists a delta greater than 0 such that for every partition P with norm mu P less than delta, here there exists a delta greater than 0 depending upon epsilon. This thing depends upon epsilon. Whatever the epsilon you are taking, that thing depends upon that. Depending on epsilon, because we already chosen a condition like this, 2k p minus 1 delta, this thing is less than epsilon. So delta depends upon epsilon. So such that for every partition P with norm mu P less than delta, what we got here, this is your UPF is less than equal to the upper Darboux integral of f dx plus epsilon. So this thing we already proved. So and your upper Darboux, since this is integrable, your upper Darboux integral equal to integral, so we can write this is your integration from a to b f dx, because upper Darboux integral is equal to integral. So we can take also here epsilon by 2 such that epsilon by 2 will be epsilon. Here we will get the epsilon. So that's why I am taking here epsilon by 2. This is so both are epsilon by 2. So UPF is, so what is the condition we got here? Here UPF, this thing is less than equal to upper Darboux integral of f dx plus epsilon. Similarly, that is also this thing we wrote for this upper Darboux integral. Similarly, for lower Darboux integral, your LPF will be greater than equal to lower Darboux integral of f dx minus epsilon by 2. So sorry, this is lower Darboux integral. Lower Darboux integral of your LPF, this thing is greater than equal to the lower Darboux integral of f dx minus epsilon by 2, since lower Darboux integral is equal to the integral, since it is integrable. So we can write this is integration from a to b f dx minus epsilon by 2. That means your LPF, this thing is greater than equal to your lower Darboux integral of, simply integral of f dx minus epsilon by 2. So if I will multiply, this is your LPF is greater than equal to this one. So if I will multiply minus sign here, then minus of LPF, this thing is inequality will be changed. This thing will be less than equal to minus of integration of f dx plus epsilon by 2, and this is your first one, this is your second one. If I will add both the things, so 1 plus 2, if we will add by respective sides, so your UPF minus LPF, this thing will be less than, simply there is epsilon by 2 here, so this thing will be less than epsilon, because this is your only the integral is there. We already removed the upper Darboux integral, so this is the only integral. So this is in plus sign and this is in minus sign, so both these things will cancel out, so only epsilon by 2 plus epsilon by 2 will left. This is your epsilon. So this thing proved. So if f is integrable, then UPF minus LPF is less than epsilon. So now comes to the backward part or the reverse part. So what will be your reverse part, or we can say this is a sufficient part. Now this condition is given, that means given that UPF minus LPF is your less than epsilon, and whatever the partition P is a partition where P is a partition, such that norm mu P, this thing is less than delta, and this delta depends upon epsilon, whatever the epsilon we are choosing. Now we already know these things. For any partition P, we know that LPF, this thing is less than equal to the lower Darboux integral of f dx, which is less than equal to the upper Darboux integral of f dx, which is less than your UPF. So if we will take their difference, the middle one's difference, that means your upper Darboux integral of f dx minus lower Darboux integral of f dx, this thing will be less than UPF minus LPF. And you know your UPF minus LPF, this thing is given, this is less than epsilon or less than equal to epsilon, whatever it may be. So this is less than epsilon. So since this one is a less than epsilon, then you can write your upper Darboux integral of f dx minus lower Darboux integral of f dx, this thing is less than epsilon. And you know since this thing is always less than equal to this one, so this thing is always non-negative, that means we can say this thing is 0 less than equal to this one. Already this one is less than equal to this one. So if we will make the difference from larger one to the smaller one, so whatever you will get, this will be, if they are equal then it is equal to 0, if they are not equal then it will be greater than equal to 0. That means finally this is 0 less than equal to this thing, and this thing is less than epsilon. And what you know about epsilon? Epsilon is a very small positive number. Epsilon is a very small positive number, and since this is a non-negative number, this difference is a non-negative number because it is greater than equal to 0. This is a non-negative number which is less than delta, which is less than epsilon, where epsilon is very small arbitrary positive number, very small arbitrary positive number. Thus we can conclude that this thing is equal to 0. That means if you will take any small positive number, it is always less than that. That means its value is equal to 0 and it is never be negative. So we conclude that upper Darboux integral of f dx minus lower Darboux integral of f dx, this thing equal to 0. This implies the upper Darboux integral of f dx is equal to lower Darboux integral of f dx. So this is the proof. Thus we can say f is integrable. Since lower Darboux integral equal to upper Darboux integral, this implies your f is integrable. It was the question, if a lower Darboux UPF minus LPF is less than epsilon, then we show here that f is integrable or f is Riemann integrable. F is Riemann integrable. Similarly, also we can, this is proved. So if we will go on to next, then there is some deduction. Deduction means okay, write down it. Suppose f is a function over f is integrable over closed AB. if f is integrable over close AB, or f is integrable over close AB if and only if there is a number, if and only if there is a number I lying between, there is a number I lying between LPF and UPF such that for every epsilon greater than 0 there exists a partition P, there exists a partition P of closed AB such that UPF minus I modulus is less than epsilon and I minus modulus of I minus LPF is less than epsilon. That means f is integrable. You can say this is for already. F is integrable on closed AB if and only if there exists a number I lies between LPF and UPF such that for every epsilon greater than 0 there exists a partition P of closed AB such that UPF minus I modulus is less than epsilon and I minus LPF modulus is less than epsilon. So if we'll go to its forward part, so what is given? F is integrable. Given that f is integrable, so if f is integrable, so what we proved in our last theorem, given that f is integrable, so there exists, or so for every epsilon greater than 0, so for every epsilon greater than 0 there exists a partition, P, there exists a partition P of closed AB, there exists a partition P of closed AB such that your UPF minus LPF, UPF minus LPF, this thing is less than epsilon. This thing already we proved in our last theorem. So if your UPF minus LPF is less than epsilon and I is a number lying between LPF and UPF, so we can write here UPF minus I plus I, just I will minus I plus I if I will make this operation. So if this thing is less than epsilon, then your mod of UPF minus LPF, this thing will be less than epsilon. Now I will add plus I and minus I and plus I. So this is your UPF minus I plus I, then minus LPF. This modulus is less than epsilon. Similarly, this is the mod of A plus B. So you can write it as mod A plus mod B. That means this is your UPF minus I plus I minus LPF. This modulus is less than epsilon. So modulus of this one plus modulus of this one is epsilon. So what can you say? You have to prove okay, we just write in different. So UPF minus LPF, or the mod of UPF minus LPF is less than epsilon. I have to show these things. That means that UPF minus I is less than epsilon and I minus LPF is less than epsilon. So what will be your UPF minus I? UPF minus I, since your I is lies between LPF and UPF, and you know the difference between UPF and LPF is less than epsilon, so we can say UPF minus I, this thing is less than your UPF minus LPF, and your UPF minus LPF is less than epsilon. This implies your UPF minus I is less than epsilon. Similarly, your I minus LPF, this thing, since this is your I, this is your LPF, so I minus LPF, this thing is less than your UPF minus LPF, which one is less than epsilon. So this thing holds. So if we'll go to the reverse way, so for reverse way, this thing is given, that means your UPF minus I modulus, this thing is less than epsilon, and this I minus LPF, this thing is less than epsilon. So if we'll add these two things, or if we'll say consider UPF minus LPF mod. So if this mod is less than epsilon, then you will say that f is your integrable by your previous theorem. So what will be your UPF minus LPF? This thing is equal to your UPF minus I plus I minus LPF. And if we will take the modulus, then this will be less than equal to mod of this thing plus mod of this thing. And individually this one is less than epsilon, and also this one is less than epsilon. That means this is your 2 epsilon. So you can take it as epsilon 1. So taking 2 epsilon equal to epsilon 1. So here what we got here, now here UPF minus LPF modulus is less than epsilon 1, thus f is integrable. Thus f is integrable. So this is the proof. Then it has also some properties. The Riemann integral, has some properties like suppose f1 is a Riemann integrable on closed AB, and similarly suppose f2 is a Riemann integrable on closed AB, then your f1 plus f2 is also a Riemann integrable on closed AB. Similarly, f1 minus f2 is also Riemann integrable on closed AB, and also their product is also Riemann integrable. If we will take the product or division, these things are also Riemann integrable. Okay, only plus and minus are given here. Okay, so this thing, this algebraic properties holds. So if we'll go to next theorem, okay, just say it. If f is bounded and is integrable, if f is bounded and is integrable, if f is bounded and integrable on closed AB, then mod f is also bounded. This thing is also bounded and integrable, and if you will take their modulus, sorry, integration of f dx from a to b whole modulus, this thing is less than integration from a to b f dx. You know, integration means this is just a summation, so whole summation is always less than the individual summation. So this thing we have to prove here. This is the third one, and in the second one we have to show mod f is integrable, and in first one we have to show mod f is bounded, and the given condition is f is bounded. So I will go through it. Since are given that f is bounded, and it is integrable, f is bounded, that means your f of x modulus, this thing is less than equal to k for all x belongs to closed AB, since everything is on closed AB. So since f of x is bounded, so mod f of x is less than equal to k for all x belongs to close a B. So since your mod f of x is less than equal to k, so you can say your mod f of x is bounded, because mod of x is given, this is less than equal to k from this condition. So mod f of x is bounded. So the first one is proved easily. So now we'll show how the mod f is integrable. So if f is integrable, so how we'll conclude that your mod f is integrable, given that f is integrable. So since f is integrable, so there exists a partition P such that UPF minus LPF, this modulus is less than epsilon. So if this thing is less than epsilon, consider a partition. So this thing is less than epsilon for a partition P, and the partition is your A is x0, then x1, x2, dot xn, which is equal to B. And similarly, now we will write the maximum and minimum, supremum and infimum values of f. Let capital Mi, small mi, and capital Mi dash and small mi dash are the, since f is bounded, so since f is bounded, so all the f is bounded and mod f is also bounded. So if we will consider any of its subinterval like your xi minus 1 to xi. So since f is bounded and mod f is also bounded, so in any subinterval xi minus 1 to xi, so both the functions are bounded. So I will write the supremum and infimum values. Let capital Mi, small mi, capital Mi dash, small mi dash are the supremum and infimum of f of x and mod f of x respectively on this ith subinterval on xi minus 1 to xi. So on this subinterval, suppose these are the supremum and infimum values. So after knowing this thing, what we will do now, for x1 comma x2 belongs to xi minus 1 to xi. Suppose in this subinterval x1 and x2 are 2 points, then f of x1 minus f of x2, this is mod of f of x1 minus mod of f of x2 whole modulus, and this thing is equal to, this is your mod f of x1 means this is your f of x1 mod. Similarly, this is your f of x2 mod, this thing whole modulus. So this thing whole modulus, this thing is less than equal to your f of x1, which is f of x1 minus f of x2 whole modulus, because we know a plus b modulus is less than equal to mod a plus mod b. Similarly, when it is a case of minus, then this inequality changes. That means your a minus b whole modulus, this is your mod a greater than equal to mod a mod b. So this one is your mod of f of x1 minus f of x2, mod of f of x1 f of x2, this thing is greater than equal to their individual modes difference. So this is your less than equal to f of x1 minus f of x2 whole mod, and this one will be your capital Mi minus small mi, and what will be on the left hand side, this is the mod of mod f of x1 minus mod f of x2, and I have already told you that this is the maximum and this is the minimum. So that means your capital Mi dash minus small mi dash, this thing is less than capital Mi minus small mi. And also we did these things previously. Your UPF minus your LPF, this thing is always less than your capital Mi minus small mi. If f is a function over the partition P and capital Mi is the infimum, this thing whole into B minus A. This thing we already proved before. So if you will get this thing, again if you will multiply suppose Mi dash minus small mi dash whole into B minus A, this thing will be similarly capital Mi minus small mi whole into your B minus A. And you know this is for partition P for the function mod f. So that's why your U P mod f minus L P mod f, because these are the conditions we already draw for UPF minus LPF. So this thing is for P and mod f. So this thing is less than this one. So we can write in place of this one, and again this one is less than your UPF minus LPF. That means this one is less than this one. Similarly, if you write this thing for mod f, UP mod f minus LP mod f, so this thing will also less than capital Mi dash minus small mi dash whole into B minus A. And here it is saying that this one is greater than this one. So similarly, you can say this one is greater than this one. So that's what I wrote here. So and we know UPF minus LPF is less than epsilon, since it is integrable. Already given that f is integrable, so the right hand side is less than epsilon. So you can say your LP mod f minus UP mod f minus LP mod f, this thing is less than epsilon. Thus we can say mod f is integrable. So now mod f is integrable. The second thing we proved. Now what is the third thing? Their modulus will be less than, and we know this thing. So mod f is integrable. Then third, we know f and minus f both are less than equal to f. That means if f is any function, so both are less than mod f. Mod f is always positive. Okay, so f is any function, mod f is always positive. So if you will take f or minus f, so both are less than equal to mod f. Since both are less than equal to mod f and both are integrable, so this implies we can write here integration of f dx, this thing is less than equal to integration of mod f dx. This is from A to B. Since this one and this one both are less than this one and all are integrable, so I can take the integration of both sides. And since f and mod f both are integrable, so I can take modulus of this one, so that individually I will not write this thing is less than equal to mod f dx, and integration of minus f dx, this thing is less than equal to integration of mod f dx. So individually we can write these things, these two things. If in a single line I will write this thing, this is the mod of whole mod of integration from A to B f dx, this thing is less than integration from A to B mod f dx. So this is the thing. Since we know f and mod f both are less than equal to mod f. So these are all things. Thank you.